Hi there, let's with the next or third way that heat transfers, and that is through empty space or without particles. Remember, conduction, we need solids. Convection, we need fluids, which are liquids and gases, while radiation travels without particles. There are different types of radiation that we need to be aware of, strong and weak. So let's look at that. Let's go to the strongest end of the electromagnetic spectrum, which is another way of saying radiation, and we're looking at gamma rays. Example would be nuclear bombs. Gamma rays are deadly to us and they're very powerful. The second most powerful type of radiation is X-rays. Then the sun's light, which is UV light. Then there's the visible light spectrum. Then infrared radiation, which comes from heat waves, like heat lamps. Then there are different forms of radio waves, microwaves, TV, FM, AM, and cell phone. And these are the weakest. So what distinguishes a weak from a strong type of radiation? Well, radiation usually travels in waves. And we use something called the wavelength to help determine whether radiation is strong or weak. The longer the distance between one hill of the wave and another is the wavelength. And weak radiation has long wavelengths. Powerful radiation has really short wavelengths, which means the distance from one hump to another is really close. So weak radiation has long wavelengths. Strong radiation has short, tiny wavelengths. So given that, here's what AM radio would look like. Television, microwaves, infrared, visible light, UV light, X-rays. You can see how much more powerful they are and how their wavelengths look. Cell phones, are they really dangerous? Well, there's more and more research to say maybe even though the wavelength of a cell phone is quite long, that maybe these types of radio waves over long periods of time might be dangerous to our brain tissues. Let's talk more about what we should know about radiation. Here's an experiment we did where we compared two different types of cans. One was black and the other was white, to see how infrared, that's the heat lamp here, infrared radiation is affected by these two colors. And so we timed for 10 minutes how hot each of the two cans got. And what we should have found out was the black can definitely heated up faster, which means black colors absorb radiant energy a lot more than white. Some other things, we know that there are different types of radiation. They travel in waves. They're very fast moving and they're absorbed by certain types and reflected by others. So dull, dark objects absorb radiant energy, whereas white, shiny objects reflect radiant energy better. White, shiny objects. We should be familiar with how UV light works. As you know, UV light is pretty strong type of radiation, and so we want to make sure that we use sunscreen so we don't get too exposed. Let's look at a thermos for a minute. Inside a thermos, if you've ever lifted up the lid, you'll notice that the inside is really shiny and mirror-like. And that's to help keep thermoses hot. So what happens is, whatever our hot liquid is, it will give off heat, and the heat bounces off the inside of the walls and stays warm. Let's talk about polar bears. Polar bears live in the Arctic, and You'd think that they would want black skin so that the black absorbed the UV light a lot better. Well, they actually do have black skin, so their hair strands are whitish, but the skin itself is black, so it does actually have black dark skin to absorb UV light. Let's look at this video clip on radiation.
Eureka! The story so far. Whenever there is movement and friction between two objects, you get heat. This is because the movement of molecules and heat are really one and the same. But we know that movement is a form of energy, so it follows that heat itself must also be a form of energy. That's why heat, just like energy, is measured in joules. And now, radiation waves. If you touch something that is very hot, you'll get burnt. This is because of conduction. The heat is conducted by a sort of domino effect from molecule to molecule, or from atom to atom, along the hot object and into your fingers. That's one kind of heat transfer. But if you hold your other hand above the same hot object, you will also get burnt. This is because of convection. The hot object causes the molecules of air above it to speed up. The hot air expands and becomes less dense, and is therefore conveyed upwards. That's a second kind of heat transfer. Are these the only two ways that heat can be transferred? Then why are you sitting under that beach umbrella? Because the sun's too hot? But how can the sun transfer heat to you? You're not touching it, so there can't be any conduction, can there? And since most of the space between you and the sun is just that, space, except for the thin layer of air formed by the Earth's atmosphere, there can't be any convection either, can there? Because once you get beyond our atmosphere, there's almost nothing out there to do the convecting. But the sun still feels hot. Amazing. How is that possible? Is there a third kind of heat transfer which allows heat to move through empty space? Yes, there is. And to understand it, you must first of all remember that heat is a form of energy. Now, energy can travel in various ways, but one of the chief ways in which heat energy travels is in the form of waves. Rather like the waves that a boat makes when it moves through the sea, or the waves that spread out when you drop a pebble into a pool of water, or the waves that travel along a rope if you jiggle one end of it up and down. In all these cases, what you are seeing is the effect of the movement of energy itself. By means of waves, energy can move through any distance. You can do it yourself. You can make that umbrella move without touching it. Tie one end of your rope to the umbrella, and now move your end of the rope up and down. You can actually see that your energy is traveling through the space between you and the umbrella, and then making the umbrella move. The heat energy from the sun travels like that. The sun sends out waves of heat energy in all directions. Each of them is rather like the spoke of a wheel, and this is exactly what scientists call them, only they use the Latin word for spoke, which is radius, from which they get the word radiation, the name given to this third kind of heat transfer. So it's by means of radiation waves that the sun can transfer its heat energy to you, and make your molecules go faster, and therefore make you hotter, even though the sun is millions of miles away. Just as, by means of waves again, you can transfer your energy to the umbrella and make it move, even though you're standing several meters away from it. But it isn't just the sun that radiates heat in all directions. So does an ordinary fire, or a stove, or an electric light bulb. In fact, waves of heat energy are radiated to some extent by all sources of heat. Even you radiate a certain amount of heat in the form of waves. Come to think of it, there are waves everywhere. Oh, watch out. Here comes a big one now.